Hi, everyone, and welcome to this episode. Today, we are studying for the AP Chemistry exam, and specifically, we're looking at Unit 2, Molecular and Ionic Compound Structure and Properties. Back in Unit 1, we spent some time learning about atomic structure and isotopes and electron configurations and periodicity, about basically everything we need to know about the single atoms themselves and where they're located on the periodic table. Here we start looking at the atoms and how they start joining together to form chemical bonds. And it's a short list of topics. We're going to do types of chemical bonds, the intramolecular force, which is different from intermolecular forces, that'll be in Unit 3, and potential energy, the structure of ionic solids, the structure of metals and alloys, Lewis diagrams, that's my favorite, drawing molecules, it's the best, resonance and formal charge, and Vesper theory and bond hybridization. So, not a huge list of topics, but we're going to get through them. First, let's talk again about electronegativity. Electronegativity was outlined in Unit 1.7. It's one of our periodic trends, and it's based on what's happening inside the atom, Coulomb's law, attraction of electrons to protons, and repulsion of electrons between themselves. And so electronegativity values can be used to predict the type of chemical bond between two atoms. And I've got a little electronegativities chart here. And these are not numbers you'd have to memorize, but you should know the general trend that the lowest ones are down here on the lower left, and the highest electronegativities are up there on the upper right. So a nice diagonal pattern. It's not a perfect pattern, but it's a nice general thing. And in general, the farther apart atoms are along that diagonal, the bigger the difference in its electronegativity. So, and that's the big component in determining what type of bond it actually is. Sorry about that. So let's start with nonpolar bonds. Let's say we get a couple of atoms together who join up to make a chemical bond, and they have very similar electronegativities. You might think maybe a carbon with another carbon, they would be the exact same electronegativity. Or maybe a carbon with a sulfur, 2.5, 2.6. They're pretty equal. And what's going to happen is because they're similar in electronegativity, the tendency of electrons to gravitate toward them, they end up making nonpolar bonds. They kind of share equally between the atoms. And so the electrons being shared kind of hang out in the middle and are not really controlled by one atom more than another. Okay, so that's nonpolar bonds. Generally, anything with a difference between 0.0 and maybe 0.4 difference in electronegativities, you have to subtract those numbers if you have them. Otherwise, just kind of guess by their position on the periodic table. Polar bonds. What happens if you get two atoms together and one of them is much more electronegative than the other one? So, unequal electronegativity, the atom with the higher electronegativity will develop a partial negative charge relative to the other atom. So, for example, between hydrogen 2.2 and iodine 2.7, the iodine not only has a greater number of electrons to begin with, a greater electron density, but also it's going to pull the bonding electrons closer to it. And so we end up with the iodine being more negative. It's not a full negative. Notice it's like a little D minus. That's the Greek letter delta. And there's a little D plus. That means partial positive, partial negative charge. But the idea here is that it's lopsided and it's polar. So they're a little bit farther away from each other on the periodic table, and so we would predict a polar one. In single bonds, the greater difference in electronegativity lead to greater bond dipoles. And it should be noted that all polar covalent bonds are a little bit ionic in character. And that's because the electrons keep moving. They're always moving. And there might be an instance where all the electrons have moved over to the one atom and you actually have a full ionic charge. And it might be momentary. It might go back to being a partial charge, positive and negative. But there's kind of a continuum in terms of kind of sliding toward polar, and then getting into ionic. All right, generally speaking, bonds between a metal and a nonmetal are ionic, and bonds between two nonmetals are covalent. Let's go back here to this one again. If you have a metal, something over in this range, it's got a very low electronegativity, and these tend to have high electronegativity. So you get one of each, it's probably going to be ionic. Again, it's a continuum, but most likely ionic. Whereas if you're bonding things just between things over here, it'll generally be a covalent bond where you're sharing electrons. In an ionic bond, there is no sharing. One just gives away the electron to the other one. All right. And College Board tells us, and this is true, examination of the properties of a compound is the best way to characterize the type of bonding. If you understand the properties that go with different types of bonds and you do some chemical tests on them, you can kind of guess, I think that's going to be a nonpolar covalent bond compound, or maybe this is a polar covalent compound or an ionic. And let's talk quickly about metals before we move on. In a metallic solid, the valence electrons are considered to be delocalized. What does that mean? It means they're not really held by any particular one metal atom. These metal atoms give up their electrons, and those electrons just kind of float around in this sea of electrons, randomly moving between all of the particles, the cores, the metal cores. And that gives rise to some of the properties of metals, the fact that they're malleable. You can whack them into different shapes because the sea of electrons kind of keeps them together. It conducts electricity, and so on. All right, so let's get that. I'm going to show you a graph. And this is a super important graph. I always tell my students, you're pretty much guaranteed to see a graph like this on the AP exam somewhere. Probably a multiple choice, but I can't rule out an FRQ as well. And what it is showing is it's showing the energy of a pair of atoms as they get together and form a chemical bond. And you have to kind of read it from right to left if you want to follow the formation of a chemical bond. Big topic, big idea. The formation of a chemical bond always releases energy. Formation of bonds always release energy because when the atoms are by themselves, kind of like when people are by themselves, it's kind of a high stress situation and it's tough to be on your own. But then maybe you find your person and you sort of settle into a more calm, restful, lower energy place because it's not as stressful. So atoms are kind of like that. They like to be in a lower energy place, and so they do that by overlapping their orbitals. So imagine a couple of atoms that are far apart from each other, and they start moving toward each other. And as they do, they sort of give in to the attraction that they feel for each other. Maybe you've had that experience too. And you move, and they give off the excess energy that's sort of keeping them apart, and they settle into sort of a low energy place. Okay, and that happens when their sort of orbitals are overlapping a little bit. And this spot right here on this graph is the really important part because what it tells us is, number one, how much energy per mole of these bonds, usually it's in kilojoules per mole, is released when a mole of those bonds is actually formed. In this case, it's a little bit over 432 kilojoules. Okay, and it also tells us down here the distance between the nuclei, the internuclear distance. And it tells us the bond length. Okay? And you might be wondering, okay, they go to a lower energy place. Why does it shoot up like that, like kind of like asymptotically? And you might wonder why that happens. Well, it turns out that the nuclei, the bond length is sort of where we get this happy medium, this sort of a balance. The nuclei repel each other, but the electrons between them are holding them together. And so you have this sort of balance of repulsion and attraction. If you push the nuclei too close to each other, they're not going to like that at all. They're going to repel each other a lot. And so it takes a lot of energy to do that. And so that's why the energy would have to go way, way, way up if they got even closer than that. So that's kind of the shape of that graph. Two useful pieces of information: the bond energy and the bond length can be determined from a chart like that. Again, you're pretty much guaranteed to see one of those on an AP exam. Okay, let's talk about the actual values. In a covalent bond, the bond length is influenced by both the size of the atom's core and the bond order. And what we mean by that is whether it's a single, double, or triple bond. You can't go beyond triple, doesn't happen. Bonds with the higher order are shorter and have larger bond energies. All right, and I have a couple of charts. Just these values, you do not have to memorize those. If you ever needed them, you would be given those in some sort of little table in the prompt. But take a look for a moment. We got carbon-carbon single bonds, and this is in bond length. It's in a weird unit called an angstrom. That doesn't matter so much. It's more the magnitude of the things here. And an angstrom is about 100 picometers. So if we put the decimal point over 2 spots, we'd get picometers. All right. So the carbon-carbon single bond is longer than the carbon-carbon double bond. which is longer than the carbon-carbon triple bond. So as the bonds are getting higher order, they get closer together, the nuclei do. That's because there's more electrons in them holding those nuclei together, and there's a lot more attraction, and so the bond length gets shorter. Same with the nitrogen, single, double, triple, they're getting shorter, and oxygen, single, double, they're getting shorter. Okay, and here's a chart of bond energies. Again, if you need these, you'll be getting them. For example, if you want to find the enthalpy of a reaction, you can actually add up the bonds that are broken minus the bonds that are formed. We'll do that in Unit 6 on thermochem. But this is where a table of values like that would come from. And again, notice, you kind of jump around here a little bit. Carbon-carbon single bond is only 348 kilojoules per mole, whereas a carbon-carbon double bond is 614, and a carbon-carbon triple bond is 839. So if it hopefully it makes sense, if one pair of electrons releases some energy, adding a second pair doing the same thing, and adding a third pair, you'll get higher and higher bond enthalpies. Okay, and I'm going to show you a question. It's fairly popular on AP exams, and it's just this modest, unassuming, multiple choice question. Which of the following has the largest bond energy? And you might think to yourself, oh, well, I know my bond lengths and I know my bond atomic radii chart. And I might think to myself, oh, well, let's see, I'm looking down the list and I'm seeing fluorine here. And fluorine here is the smallest of the atoms in terms of its atomic radius. So it might be tempting to think, well, the two fluorines are going to get really close to each other and have a very short distance and a larger bond energy because they're getting closer to each other. Well, that's true if all of these were single bonded to each other, but they're actually not. And it may be helpful when you see a question like this to just sketch their little Lewis structures. If you sketch fluorine, you would find out that it is, yes, indeed a single bond. And chlorine is also a single bond between them. And iodine is also a single bond between them. But when oxygen and nitrogen get together, they actually do not form single bonds, they form double bonds. So like right now, you're breathing in oxygens from the air, and those oxygens are double bonded to each other. That's the only way to make 10 electrons fit for both elements, both atoms. And nitrogen, I'm going to slide it over here. Actually, so sorry, that was 12. Nitrogen has 10 electrons, and the only way to make it work for both atoms is to make a triple bond. So nitrogen is triple bonding. Yes, you're breathing that in, you're breathing it out. Your body doesn't know what to do with it. But it's triple bonded, and that means it has the largest bond energy of all 5 of these. So yeah, it looks like it's one answer, but buried underneath it are these double and triple bonds. It would also be the shortest bond length because it's triple. Maybe that's the second one and its other ones. This would be the shortest bond length of the 3 single bonded ones because iodines are very large. They would have a larger bond length between them. All right, so watch out for that question when you see it. All right, quickly, let's talk about Coulomb's law. And Coulomb's law can be used to understand the strength of interactions between cations and anions. And so it appears you probably get 2 or 3 questions on an AP exam regarding Coulomb's law. And it goes like this. There's a constant in there. There's several versions. But what you really need to know is you're not going to have to calculate anything. But you should know that Q1 and Q2 are the charges of the ions, maybe a +1 and a -1 or a +2, -2. And the R stands for the distance between them. Okay, distance between those centers. And in general, though, here's what you need to know. The higher the charges, if you're comparing ionic compounds, the higher the charges lead to stronger interactions, and smaller ions lead to stronger interactions as well. They get closer to each other. So the force between them is proportional to the charges that are there and indirectly proportional to that R squared. Okay, so here's another quick question. Which of the following would be expected to have the largest lattice energy for an ionic solid? Largest energy between the ions. And we've got a list of 4 things there. And they all kind of look the same, don't they? Like sodium chloride, lithium fluoride, magnesium oxide, cesium iodide. And so you might have to think about their charges and the radii between them. So let's do this. So sodium is +1 and chlorine is -1. So 1 to 1. Lithium is +1. That's -1 as well. Magnesium, though, is +2, and oxygen is -2. Cesium is +1, and iodine is -1. And those are just charges from the periodic table that you could predict. And so I'm seeing 3 pairs of 1 and 1, and 1 that's 2 and 2. And because Coulomb's law says the force is proportional to those charges, the product of the charges, 1 times 1 is just 1, and that's true for 3 of them, but 2 times 2 is like 4. So this lattice energy is probably almost 4 times as big as the lattice energies of the other ones, because the charge plays the most important role in that. Okay, we're almost done with section 2. Here we see some general properties of ionic solids. In an ionic solid, the cations and anions are arranged in a systematic periodic 3D array that maximizes the attraction between ions and minimizes the repulsion between like ions. So they typically go cation, anion. Each one of those is attracting each other, but the sodiums and chlorines repel each other, so they're kind of a little bit further away, kind of buffered from each other by the anions or the other charged ions between them. So you get this alternating array, cation, and so on. And it kind of goes in all directions until we run out of ions, and then the crystal is that size. Note, cations are generally smaller than anions. So you're probably going to be asked to either interpret a diagram like this or draw one. And one of the things that you want to make sure that you do is, if you're drawing it, make sure your cation is smaller than your anion. And you might be thinking to yourself, wait a minute. Sodium is way over on the left, so that's where the big atoms are, and chlorine's way over on the right, that's where the small atoms are. That's true, but when they become ions, they actually change their size. Sodium lost an electron, vacated an entire energy level, and now those remaining electrons are being held tighter to the nucleus because there's more protons than electrons, so we get a tinier atom. And chlorine gains in size because now you're adding an electron, and those electrons repel each other, so they expand and get farther away from the nucleus. So be sure your cations are smaller than your anions. And now we'll move on into the structure of metals and alloys. We already saw them back in 2.2, I believe it was. And metallic bonding, so metals make use of metallic bonding, which can be represented as an array of positive metal ions, cores, surrounded by a sea of delocalized electrons. So you kind of have to imagine a piece of metal with all those metallic cores swimming in a sea of electrons, and that gets them to have certain types of properties. Metallic solids are good conductors of electricity and heat. And that's because you've got these mobile electrons that can carry electric charge from one place to another, and they can bring energy and heat from one end to the other. And they also tend to be malleable and ductile. Ductile is that word we use that we can draw them into wires. We can stretch it out because those metal cores can kind of slide past each other, and they're still held together by that sea of electrons. And we already talked about malleability, being able to use a mallet and whack it into different shapes. All right, here we get our first glimpse at alloys. They will appear also in Unit 3, but here we go. Alloys are mixtures. They're not compounds. That's a very important distinction to make. They're not actually making chemical bonds between them. You're just mixing the metal cores to some degree or another. And an alloy can be in any composition. So this is one of the things that distinguishes it from a chemical compound. A compound always has the same percent composition because the number of atoms in each molecule is the same, or in an ionic compound formula unit. But in a metal, you can swap in as many of one as the other, and there's a huge range of possible compositions. And so, but there's two main kinds of alloys. They can either be substitutional, in which the atoms are of similar size, and they can just sort of swap in. Like this one right here is sort of a similar size, but maybe it's a different element. Maybe it's copper and zinc or something like that. You can just swap them in. Sometimes, though, as in the case of, for example, carbon steel, you can add another element to the metal, and it's so small it just takes the spot in between those ion metal cores. That's the interstitial space. And so it actually makes the alloy harder. Carbon steel is stronger than regular steel because the carbons sort of inhibit those metal ions from traveling against each other and moving past each other, and you get a harder alloy out of that. All right, now we're coming up to my favorite part of this unit, and that is drawing Lewis diagrams. So what are Lewis diagrams? Lewis diagrams are drawings. They're models that we use to represent molecules. Molecules don't actually look like this, but they help us to sort of give us a framework as to what is attached to what and where any extra electrons might be. All right, and that's crucial for the next step, which would be to anticipate its geometry, its bond angles, whether it's polar or not, and so on. So Lewis structures are simply drawings of molecules, and they can be constructed using an established set of principles. So what I'm going to show you now, if you feel like pausing the video and writing this down or taking a screenshot or something, this is my wording. You might have a document that has similar wording somewhere, and there's a couple of different ways to draw Lewis structures, but I find that this is the most straightforward, repeatable, and let's go get it. First, there's going to be 5 steps. The first 3 you are going to need, and then when you get to steps 4 and 5, you get to choose. Maybe you'll do step 4, maybe you'll do step 5, maybe once in a while you'll do both. But here we go. Sum the valence electrons for all the atoms. Use the periodic table to help you do this. If the molecule is neutral, we're going to simply add up the total valence electrons. If the molecule is an anion, we're going to add an electron to the total for each negative charge. If the molecule is a cation, subtract an electron from the total for each positive charge. So we'll get to an example of that. Then we're going to draw the skeleton structure. Okay, for simple molecules, generally speaking, the one that's listed first is going to go in the middle. The one that's listed second or third, they're going to go around the outside, and we're going to connect them to the center using single bonds. If hydrogen is listed first, like in an acid, don't put that in the middle. Hydrogen does not go in the middle. Put the next element in the middle, like HNO3. The N would be in the middle as opposed to the hydrogen. Start with the outer atoms and give them all enough electrons to make an octet. Okay, here's the first time we see the word octet. You might have heard about the octet rule, which is the tendency of atoms to end up with an octet or 8 valence electrons in a molecule. Maybe it doesn't start out with 8, but it wants to end up with 8. Hydrogen is an exception. Hydrogen tends to follow what we call the duet rule. It only has 1 valence electron to start, and so it's going to pair it up, and then it's done, because it's a tiny atom and it can't fit anything else around it. Step 4, if you have leftover electrons, place them on the central atom in pairs. Do this even if the central atom ends up with more than an octet. We'll see an example or 2 of that. And then once in a while, you'll run out of electrons. If there are not enough electrons to give that central atom an octet, here's where we actually make them do double duty. We swing them in toward the middle and make a double bond or a triple bond or maybe more than one of each. But yeah, those are the steps. So we're going to try to practice them. I'm going to start with one of my favorites. Draw the Lewis structure for SF4. And all right, let's do the steps. Sulfur is in column 6A or column 16 of the periodic table. So it's got 6 valence electrons. Fluorine is in column 7, second to last, and there's 4 of them. So that makes 28 and 6. That gives me 34 electrons. So in my drawing, I have to have 34 electrons shown. So let's put the sulfur in the middle. Let's put the fluorines around the outside. It really doesn't matter where you put them. You do generally want to spread them out, though. Okay, and we're going to fill out the octets of the fluorines, which are on the outer part of the atom. And then we have to, this is step 3. Then we got to stop and see what we got. And I'm counting electrons, and I'm counting the fact that I've put 32 electrons in. Each of these single bonds represents a pair of shared electrons. So 2, 4, 6, 8 times 4 is 32 electrons. So I have 2 more to go. Where are they going to go? Well, I don't have to guess. My rules simply tell me that even if it ends up with more than an octet, the sulfur gets them, the center atom gets them. So 2, 4, 6, 8, 10 around the sulfur, and that's okay. The octet rule is more of a suggestion than it is a rule. It's true most of the time, but sometimes the central atom takes one for the team and says, I'll take those extra electrons and keep track of them for us. Okay, so now it's time for you to try one. So cover it up real quick. So take a moment. if you'd like, and pause the video and draw the Lewis structure for arsenic trichloride, AsCl3. Great. And if you came up with a Lewis structure that looks like that, with 3 bonds to the 3 chlorines and then an extra pair of electrons on the arsenic, then congratulations, that is a valid Lewis structure. So that's great. Let's try another couple. Here's one that you might see. Draw the Lewis structure for XeBr4. And you might be sitting here thinking, whoa, wait a minute, Mr. Rudolph. I've been paying attention in chemistry class, and my chemistry professor says that noble gases don't make compounds. They don't like to bond with anything. That's why they're noble gases, right? That's true for the most part. However, if it's with another atom that's very electronegative, like bromine's pretty electronegative, the electronegative atoms can kind of force the noble gases to bond with things. And so you might see one. And when you do, make sure it starts with 8 valence electrons. It's probably going to end up with more. 7 valence electrons times 4, that's 28 plus 8 is 36 electrons. And then you follow the same steps just like before. So we're going to add the bromines around the outside. 6 more electrons to fill out their octets. Make sure I can see that one. And again, I got 32 electrons, 4 more to go. They simply don't guess. They just go on the central atom. And we end up with 4 bonds and 2 lone pairs on that central atom. Come back to that in just a second. I did want to try one that has a charge to it so that you get to see an example. This is a very common one, nitrate ion. And okay, so we're going to follow the same steps. Nitrogen is in column 5 of the tall columns. Oxygen's in column 6. There's 3 of them. But then there's a -1 charge. And my rules tell me that I have to add 1 to the total for each negative charge. So that gives me 24 electrons total. That's the only new glitch. The rest of it is similar to what we've been doing. Nitrogen, oxygen, oxygen, oxygen. We'll give them all an octet. And then at this point, I would stop and say, all right, I finished step 3. Now, how am I doing? I've just used up all 24 valence electrons. I don't have any more to go. If I ran out, I do have to check that central atom. Did you notice that the central atom does not have an octet yet? It's got 2, 4, 6, but not 8. So here is where we start using step 5. We don't have to use step 5 all the time, but here we have a situation where we do. So what we're going to do is we're going to get rid of a pair of electrons and shift it in toward the middle and make it a double bond. Those electrons now still apply to the oxygen, but they also apply to the nitrogen. Nitrogen is happy, the whole molecule is happy, everybody's following the octet rule, and that one is done. Except for one last thing, I should note that if it's an ion, it's hard to tell where that extra electron is, or even if it has an extra electron, but we generally put it in brackets with the charge next to it to say, yeah, that is an ion. It's not just a neutral molecule. Okay, now you try one, which may or may not have a double bond or so in there. And here's drawing the Lewis structure for SO3. Take a moment, pause the video. I'll see you back here in a second. And if you did draw it, and you got something like that with a double bond on one of the oxygens, then that's great. So good job on that. Let's talk about resonance for a moment. In cases where more than one equivalent structure can be constructed, resonance must be included as a refinement to accurately predict molecular structure and properties. You might have been thinking about that when I did my nitrate ion or when you did your sulfur trioxide. Mr. Rudolph, why did you pick it to go there? Couldn't you have picked this spot to do a double bond or this spot to do a double bond? And yes, I could have. So technically, because there's 3 equivalent Lewis structures, I'm actually going to draw all 3 of them super quick. All of these are equivalent to each other. And so all of them essentially represent nitrate ion. And it's actually almost better to show all 3 of them than to just say it's stuck with one of those Lewis structures. All right, and here's where it gets fun. So resonance. Why are we using the term resonance? Well, it's kind of like it's almost related to the musical term resonance or resonating, where like a musical note might resonate and kind of bounce back and forth and kind of build on itself because it's resonating. Well, here's in molecule form that same kind of idea. There's no reason that pair of electrons needs to stay there. In fact, all these electrons are continually moving. And so it's very easy for it to jump back onto the oxygen it came from and be replaced in the middle by another one from one of the other atoms. And in fact, molecules like this have three different locations. It's actually using all three of them for brief instants of time. And they continue to go here, then here, then here, then here, then here, then here, and back and forth. And it's constantly shifting with a certain frequency and wavelength for each molecule. And that's analogous to a sound wave. And so that's why we use the term resonance. And in fact, I'm going to come back to this in just a second. When resonance is occurring, the bonding electrons can be averaged between the bonding areas, resulting in average bonds that are, over time, equivalent, shorter than single bonds but longer than double or triple, higher energy than single bonds but lower than double or triple. So let's think about this. It's going to get weird for a second. So let's imagine this nitrogen, okay? And it's got two single bonds and a double bond. Well, it's kind of like if we averaged it over time, what we would see is that we've already talked about double bonds being shorter than single bonds, but we can use spectroscopy to look at molecules like this. And what we find is that all three of the bonds are the same. Not a double and two singles, but they're the same. But we also find that the bond length is actually longer than a double, but shorter than a single. It's almost like that fourth chemical bond is sort of averaged out between the three areas. So now you've got a bond order of like 1.33 or 4/3. Okay, you might see a question about that. It's not as common as some of the other questions, but it's kind of like this idea that you're just averaging out the electrons between those areas. And so you might get a bond order of 1.33 or 1.5 or something like that. And that would be a quick little intro to resonance. Okay. All right, and now let's take a quick foray into formal charge. And formal charge is a way of kind of keeping tabs on who's got the electrons inside of a molecule and what its apparent charge is for each atom. And we can use it to sort of make judgment calls about which resonance structure might be better suited for representing the molecule. And there's a quick formula here, so maybe write it down. Formal charge equals the number of valence electrons the atom starts with, like off the periodic table, minus the number of electrons assigned to it in the atom. And that includes the number of lone pair electrons it owns while the molecule is happening, and half of whatever number of bonding electrons. So if I'm in a chemical bond with another atom, I'm going to be assigned one of those electrons, and the other atom will be assigned the other one. And we kind of do that little, add these up and subtract from the total. Formal charge can be used to determine which of several possible Lewis structures are the best. Now, I'm not going to actually calculate by hand. I'm going to have a couple of diagrams that already have them on. But you can practice this and see if you're getting the same numbers as I am. All right. So carbon dioxide, for instance. Carbon dioxide can be drawn with two double bonds or a single and a triple. Both satisfy the octet rule. They're fine. They look happy and everything's great. On one hand, though, the carbon dioxide with two double bonds, oxygens start with 6 and carbon with 4. But in this molecule, they're also assigned 6 and 4 respectively. And so the total formal charges are 0, 0, and 0. All right, the total formal charge of all the atoms should add up to the total of the entire molecule. So like my nitrate, the 4 formal charges should add up to a -1. But here they're going to add up to 0, and that's what that does. In this molecule, oxygen starts with 6, but is assigned 7, 2, 4, 6, and then one of those. And so it has a -1 charge, and that oxygen has one less than it started with, and so it's got a +1 charge. Now, yes, both of these add up to 0, but here's the criteria. The one with the lower overall formal charges, like this one, is probably the right one. That's not to say this one doesn't exist for brief instants of time, but more often than not, it's going to be this one because you have the lowest total overall charges. So you're looking for the lowest overall charges when you're doing formal charges. And let's look at another popular one. You might have seen this one before. This is the thiocyanate ion, where we have sulfur, carbon, and nitrogen. And there's three ways to do that as well. You can do a triple and a single, double and a double, or a single and a triple. And if you can see these formal charges, we have 0, 0, and -1. They add up to -1. -1, 0, and 0, adding up to -1. And then -2, 0, and -1. That still adds up to -1, but these magnitudes of charges are bigger. So I'm probably going to omit that one and just say that's probably not going to be the right one. So how do I decide between these two if they both have the same magnitude of formal charges? Well, the way to pick is to try to get the negative charge, if there is a negative charge, on the most electronegative atom that there is. And so both of these are probably happening at some point or another, but since nitrogen is more electronegative than sulfur, generally pick that one to have the more negative charge attached to it. So just a general idea in case you ever see that. Formal charge is not on, I don't think, every AP exam, at least not that I know of. It's probably in the multiple choice, maybe. But yeah, there are some limitations to the Lewis structure model, particularly in cases where the molecule has an odd number of electrons, such as NO2. I just talked to my students the other day, and on the 2024 exam, there was actually a Lewis structure for NO2, which, if you add up, has 17 electrons, 12 from the oxygen and 5 from there, and it ends up having a single electron where there should be a pair of electrons, but it's a single. And it doesn't happen all the time, but you might occasionally see it. So there's some drawbacks there. All right, let's talk about valence shell electron pair repulsion theory, VSEPR. I like to say Vesper because it just sounds easier. I know it's not spelled like that, but it's just easier to say. And bond hybridization. So Vesper theory uses Coulombic repulsion between electrons as a basis for predicting geometry. Bonding pairs around an atom will arrange themselves to gain maximum space and minimal repulsion. Let's go through this pretty quick. You should have a chart of these. If not, there's tons of them on the internet to go and get. I will tell you that there's 5 main what we call electron pair geometries. You can fit 2 pairs around a central atom, 3 pairs, 4 pairs, 5 pairs, and 6 pairs around a central atom to get these geometries. So, and they have names like linear, trigonal planar, tetrahedral, trigonal bipyramid, which is kind of like a 6-sided die, and then an octahedron if you connect all the corners of these 6. And so they all fall into those categories, main electron pair geometry. But in each one of these, there's actually some subcategories as well. And these would be the molecular geometries. These are the ones you're going to be asked about way more often. So you can have 4 bonds, and which makes a tetrahedron, a tetrahedral. Or what if there's 3 bonds and a lone pair? That lone pair also needs its space and will repel the other ones. It'll actually be held closer to the central atom because it's not being shared with anything. And so it shoves everything off to one side, and the bond angles are getting smaller. And water is a great example of something that's bent. It has 4 pairs of electrons, but only 2 of them are bonding. So it looks like a little elbow-shaped or a V-shaped bent structure with bond angles of 104.5. Okay, we're going to summarize these in just a moment. If you have 5 pairs around the central atom, they're going to repel each other and try to get as much space as possible. And what they do is they actually create a sort of a trigonal planar situation. But then there's space above and below, so you can put one up top, one on bottom, and you end up with a trigonal bipyramid if all 5 of them are connected. You could also have 4 and 1. That electron pair needs its space, so it's still occupying something. But we end up with something that looks more like a seesaw than a trigonal bipyramid. That's my favorite one, by the way. And if 2 of those get taken off and you're left with the lone pairs, 3 bonds, 2 lone pairs, it actually forms a T-shaped molecule. These electron pairs get the 120-degree bond angles because they're held closer to the central atom and they need a little more repulsion going on. And finally, we can get 3 bonds, or 2 bonds and 3 lone pairs, which would make a linear. All right, and octahedral, you can have 3 different possibilities there. 6 bonds, 5 bonds, and a lone pair, or 4 bonds, and 2 lone pairs. And they have names that are octahedral, square pyramid, and square planar. Now, the College Board is going to give you a formula sheet. It's got all kinds of formulas on it, all kinds of constants, and they'll even label what they are. So it's nice and straightforward. There are a few things, however, that you will probably just need to know and memorize. And I hate to say that because I always say that chemistry is not really a memorization type situation, but you kind of have to know these. You're going to be asked about a geometry or 2 or 3 on your AP exam, and you're going to have to just kind of know them. So figure out a way for you to know them. I made a little spreadsheet with the different combinations of bonds and lone pairs. Their electron geometries, note there's 5 of them, and 14 or so of the molecular geometries. I also included their bond angles. As you add more and more atoms to the central atom, the bond angles get shorter, smaller, and smaller, and smaller until you get down to 90. And polarities, I included a column on polarities. Assuming all the outer atoms are the same, like all oxygens or all chlorines or something, we get general patterns in polarity. Whereas if something is symmetrical, it's going to be nonpolar. Whereas if something has lone pairs on it, generally 1 or 2 lone pairs, if you compare this column and that column, you'll get a molecule that's sort of lopsided, asymmetrical, and we end up getting a polar molecule out of that. So find a way for yourself to know those. Maybe it's flashcards, maybe it's something else, but you just kind of have to know them. Unless you're just really good and can just picture the molecule in your head. Some people are able to do that. Vesper must be used to predict the molecule geometry, bond angles, the bond energies based on bond order, the bond lengths, presence of a dipole moment, and the hybridization of orbitals. And we're going to talk about hybridization here to finish out our video today. And I included it on my chart. SP, SP2, like what the heck are all these things doing? I will start by saying we are told we only have to know the first 3, and where we start adding the D's here at the end. On the most recent College Board material, they said we're not testing the D orbital hybridizations. So that's kind of nice. We're going to stick with the first 3, though, and talk about them. Like, what is hybridization? Hybridization is, I like to use the word morphing. And it occurs when available S and P type orbitals in bonding atoms overlap and become new equivalent orbitals. And that can be arranged according to the Vesper theory. All right, here's what's going to happen. So S orbitals are spherical shaped, you got to imagine that, whereas P orbitals have sort of a figure 8 infinity sign shape to them. And they're not equivalent shapes. But when the atom says, okay, it's time for me to bond with things, I want equivalent orbitals. I want everything to be as symmetrical as possible. So what the atom will do, what the electrons in those orbitals do, is they actually change their wavelength and frequency, and they change their possible locations, and the orbitals actually change. An S orbital doesn't exist anymore. That P orbital doesn't exist anymore. They've merged into 2 identical orbitals that are kind of like hybrids of them. Let's look at a couple of pictures. And I should start by saying only the number that are needed for bonding do this. The rest of them kind of stay as their own typical atomic orbitals. But for example, suppose you have 2 electrons and you need to make 2 bonds. What the atom will do is we'll take the S and a P, leave the other 2 P's by themselves, but they will make 2 identical orbitals. It's kind of like an infinity sign, but more like a mushroom. One side is bigger than the other. And then these 2 are equivalent, and they can sort of align themselves 180 degrees from each other and be on opposite sides of the central atom. So that's hybridization. It's deep. There's a lot of fancy math that we don't have to know, which is thank goodness. But we have to kind of know the idea. And let's say an atom needs 3 bonds, and it's got 3 valence electrons to work with. What it will do is it'll take the S first, always the S first, and then let's take 2 p orbitals and make a group of 3. 3 little mushroom clouds, and we can arrange themselves in a trigonal planar fashion with 120-degree bond angles. And the last one we need to know how to do is sp3 hybridization, where let's say carbon, for example, is needing 4 bonds. So we'll need an S, we'll need all 3 p orbitals, let's get them together, let's morph them together, and we get 4 little mushroom clouds, and they can arrange themselves like a tetrahedron, which gives us the 109.5-degree bond angles. And atoms are constantly doing this when they bond. Just for the sake of it, I'm including the trigonal bipyramid and the octahedral. These, we ran out of an s and all three p orbitals, but if I need a fifth orbital or a sixth orbital, I can reach down into the d orbitals and start morphing those. It should be noted that only things on row 3 and below are able to do these last two, because the d orbitals appear on the third energy level, and so for rows 1 and 2, they don't have d orbitals that they can bond with. Okay. So, Vesper and bond hybridization. Bonds formed when atomic orbitals overlap. In multiple bonds, such overlap leads to the formation of both sigma and pi bonds. You might not see this very often, but you should know it anyway. The overlap is stronger in sigma than in pi, although the presence of pi bonding limits the rotation of the bond and leads to structural isomers. So a sigma bond, before we look at a picture, is a bond formed between the two nuclei. So if I'm forming a chemical bond with another atom, there's electrons right between us, and that is our sigma bond, that pair of electrons. But if I want to make a pi bond, a second bond, that space in between me and the next atom is already being occupied by electrons, and they're going to repel any other electrons that get in there. So what we do is we get together and we say, all right, let's take a remaining p orbital that we're not using and morph it above and below the existing sigma bond, kind of like a hot dog bun. It's a lame way to say it, but kind of like the buns on opposite end sides of a hot dog. The pi bond is above and below the plane of the sigma bond. So let's look at a quick picture of that. So if we have a sample where we have two carbons double bonding, but then everything else is a single bond, what we get is single, 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 and then there's one sigma bond that goes between the two carbons, but now that space is occupied. So we form another pi bond above and below in order to, we're going to connect those two atoms, but we're going to use the space above and below that wasn't being used by the sigma bond. So you'll see those occasionally. Here's a very quick sample question. How many sigma and pi bonds are in the molecule? Well, it should be noted that every single bond is a sigma bond. And in every multiple bond, there's one sigma bond also. There's got to be something bonding between the nuclei. But then, once that happens, the next one is a pi bond. So I have a sigma, 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 sigma. That's 4, 5, 6, 7 sigma bonds and one pi bond. And now we're going to end this video with a quick little practice on using a chart something like this to predict molecule geometries and bond angles and so on. So hopefully you have one of those. You can peek at it if you want, or you can practice without it and just see how well you're doing. We've already drawn some Lewis structures in this episode, so let's go back and name their shapes and their geometries and things like that. So the way it works is you count the bonds, 4 bonds, 1 lone pair. That combination appears only once on a chart like this. So you find it, and that should tell you everything you need to know. Turns out with 4 bonds, 1 lone pair, it is a seesaw shape. Okay, that's great. It happens to have bond angles of 120 and 90. So if you ever actually see something in the trigonal bipyramid domain, you have to name both bond angles. Otherwise, it's going to be wrong. So sorry about that. It'll probably have those bond angles. It'll probably be polar, sort of a lopsided situation. And if you ever needed to know its hybridization, this one would actually be dsp3 hybridized. Although I've been told, like I said, that one probably won't be appearing on your AP exam anytime soon. All right, so your turn. Take a moment. You probably drew ASCL3 like this. Take a moment, see if you can classify its geometry. Great, and if you said this was trigonal pyramidal, it's going to have 107.5 degree angle, slightly less than the 109.5. This one's also going to be polar, and it's going to have sp3 hybridization because 1, 2, 3, 4 pairs of electrons, they all need a hybridized orbital. And there you go. We also drew nitrate ion. Okay, so what do we do with that double bond that I drew in here anyway? So how do you do that? Well, when you're doing shapes, count the double like a single bond. Yes, there's a sigma and a pi, but only the sigma counts for the shape. So 3 bonds, 0 lone pairs, that's going to be trigonal planar, okay, and it's going to have 120-degree bond angles. Okay, it's going to be non-polar because none of those oxygens are more electronegative than anything else, and it's going to be sp2 hybridized. S and 2p's will have the extra pi bond at the end. All right, and take a moment and try to classify that one. Back here in a sec. And if you also saw that this was trigonal planar, 120-degree bond angles, sp2 hybridized, and nonpolar, just like the NO3. And here's a fun little fact. You might have noticed a similarity between SO2 and NO2, or NO3. And that is because they have the same number of electrons in the same bonding arrangement. Okay? And when that happens, yes, the middle atom has changed, but we actually call them isoelectronic with each other. Iso meaning same, they have the same number of electrons in the same bonding arrangement, so they're isoelectronic. And just for fun, take one moment and see if you can classify this last one. And hopefully you found it. It's way at the bottom of most charts. It's in the octahedral section, but 4 bonds and 2 lone pairs is going to be a square planar shape. It's going to have 90-degree bond angles, 90 in all directions. It's going to be non-polar, so it's one of the exceptions. Usually lone pairs make it polar, but here we have non-polar. And then this would be D2sp3, but again, we're told that's not going to be on the AP exam. So if you got that, congratulations. You have mastered some Lewis structures and molecular geometries, and that concludes Unit 2. If you have any questions, send them to me directly or in the comments. In the meantime, happy studying, and good luck on the AP exam, and have a great day.